Hello everyone. First of all, I want to introduce myself. I am Betül and I am an engineer student in EMU. And today I'm going to talk about the three-phase induction motors. First of all, induction motors is invented by Nikola Tesla. And in fact, about 50% of global electric power consumption is due to the induction motors. And induction motors has two main parts, stator and rotor. And induction motor is essentially called as rotating transformer, and stator acts as a primary and rotor acts as a secondary. And the energy transfer between stator and rotor of an induction motor takes place entirely as inductive and with help of flux mutually linking the two. And now we can see the three-phase induction motor. And as I said before, we have two main parts in this motor, stator and rotor. First of all, I want to just show you the rotor part, just like this. And you can see the rotor like this. And inside of this motor, you can see the stator and winding, like this. And just here, you can see the cable connection. And just if you want the reversal of direction for rotation, you can change the cable connection. And automatically, you can change the rotating position. And as I show you, the stator is a fixed structure and is connected to three-phase supply. And basically, it's a three-phase coil winding, and three-phase alternating current is applied to windings. And it passes through this just grooves. You can just see the grooves right here. And they come together of thin steel plates like this. Inside just the outer structure made of steel or the cast iron. Like you can see here, the structure. And current passes through the windings. When a three-phase current passes through the windings, it produces a rotating magnetic field. And around the windings, this rotating magnetic field is the reason of the spin of the rotor, and we can see this shaft here also. And the magnetic field causes the just like this, the spin of the rotor, like this. And now we can see the three-phase induction motor's equivalent circuit. First of all, I want to say, and remember that we have two main parts, stator and rotor, and in this circuit you can see this. This part is a stator, like the primary part, and this part is a rotor, secondary part. And now just check the circuit. This I1 comes through the circuit. I1 is a current. R1 is a stator resistance. X1 is the stator reactance. And I1 comes through like this and divided into two parts like this. RO is of course, the resistance of the stator resistance, and XO is the reactance also. And IW and IN I have. IW is the active working component of flux, component of current, supplies, no load losses. And IN is the magnetizing component of the current. And just here we can see the E1. What is E1? E1 is the induced EMF induced in the stator in the primary part. And now we can see the air gap here between the stator and rotor. And in the rotor part, of course, we have a current also, I2R, and there is a resistance. This is a rotor resistance. And we have just here, of course, EMF induced in the rotor part. And the rotor induced EMF phase in running condition just here as E2. And we have the current here also, and X2R. What is X2R? Rotor reactance also. Just we have here the stator reactance, and this one is the rotor reactance. And we have SX2, just the relations between, and we have the current as I said before. And now actually I just wanted to draw the parts clearly, and you can see just the parts, stator and rotor. And now I want to talk about the slip of the three-phase induction motor. Slip is defined as the ratio of the slip speed between to the rotor speed. And slip is generally between 2% to 5%, and also it is defined as the measure of the difference between the machine's speed and its shaft speed. And if the slip value is greater than 1, it means that the rotor will turn in the opposite direction and to the revolution of the magnetic flux. And the slip formula is here. I can just here show over ms, and they are just the turns of the induction motor. And now let's talk about the torque production in the three-phase induction motor. What is a torque in induction motor? An induction motor develops torque by inducing current to the rotor, and which is the proportional to the differential speed of the rotor, and the rotating magnetic field inside the motor, as you can see before, in the stator. Under the condition of max starting torque, the rotor power factor angle, like I will just write the formula of this, and the rotor power factor is 0.707 lagging in the torque. And you can see just the formula here: torque power over angular velocity. This one is a power, this is the angular frequency, and this is, as I said before, it is a torque. And I just set the angles, just that one is a 45, and as I said, the power factor is lagging in the three-phase induction motor. And just here I can just write this one: I2 cos ORT is just here K I2 and cos, and this is it is the proportional to flux and per stator pole here, and rotor current, and the power factor at the rotor. You can just see this formula too in induction motor. And just a question: how can we start up the three-phase induction motor? This is the answer: that three-phase induction motor has a self-starter structure, and just we can say that when the supply connected to a stator of three-phase induction motor, a rotating magnetic field is produced, and after that rotor begins rotating, and after that induction motor starts working. Just it is the logic of the three-phase induction motor. First of all, you have to know that three-phase induction motor is a self-starting motor, and there is a magnetic field actually just produced in the stator, and the rotor begins just rotating after that. And the motor can also be started by applying a reduced voltage to the motor. And we can say that a three-phase induction motor is a basically constant speed. This is the important part: the constant speed of motor, and so it's somehow difficult to control its speed, because it is just a constant speed, and this is very hard just to control speed. The speed control of induction motor is done at the cost of decrease in efficiency, don't forget, and low electrical power factor. And we have to know the basic formulas of the speed and the torque of the three-phase induction motor, and I can just write it like this actually. This is the 1/2, and just here this is a speed, and this is a frequency, and this is just a pulse number, and you can just see the poles most of the time in the questions. Now I'm going to talk about the reversal of the direction of rotation. As I said before, we can change the rotation of the motor with the cable connection. We can change the cable connection, and just the opposite way. The motor will turn in the opposite way. We can do it, and we can do it also. It can be reversed by interchanging any two of the fifth motor supply lines. We can change the motor supply lines such that the field rotates counterclockwise rather than the clockwise, just the opposite direction, just you can see it. However, the number of poles and the speed at which the magnetic field rotates remain unchanged. And it is necessary to just change the phase sequence in order to change the direction of rotation of the magnetic field. Like you can just see you can change the phase sequence in order to change the direction of rotation. You have to change the phase sequence, don't forget. And you can do it with the cable connection also. And just if the motor is turning in the counterclockwise, your motor will turn in the clockwise when you change the cable connection or the phase sequence in the three-phase induction motors. And now we are going to talk about the power factor of the three-phase induction motor. Just like a smaller amount, like we can just see the PF like this. And the power factor, it differs between the full load or no load. It differs between them in induction motor. And induction motor draws a large magnetizing current and a small active component to meet the no load losses. Therefore, the induction motors takes a high no load current lagging and the applied voltage by a large angle. Hence, the power factor of an induction motor on no load is low. It's important. Hence, the power factor is of an induction motor on no load is very low. In no load, it is low, the power factor. And we can just see the numbers here, like or 0.90 in full load. In full load, power factor is equal to, or the power factor 0.20 in no load. As you can see, in no load it is very low, and in full load it is very high. And now I want to talk about the efficiency of the three-phase induction motor. First of all, I want to write the just formulas, and we can just talk with this. This is the formula. Just here. The efficiency. The full load motor's efficiency is about 85 between or just 97. And the corresponding motor losses are as follows: friction and linkage. And we can talk about just the stator losses in this, rotor losses and iron core losses. And you can understand that when we talk about the efficiency, we are talking about the losses, stator losses, iron core losses like this, rotor losses like this. And we can just find the efficiency from this formula: power out, power in, just multiply by the percentage of 100. And this one is the formula. And as a summary, I just wanted to say something. A three-phase induction motor has two parts, stator and rotor. And it is a self-starting motor. As you can see, I wanted to show you the motor too. We have stator and rotor, we have shaft, and we have cable connection, and we can change the cable connection just to opposite direction, just to produce the opposite direction of motor. And we are just producing the magnetic field just for the rotor spinning, And as I said before, we can change the cable connection or we can change the phase sequence just to change the direction of the spinning. And thank you for listening. I hope you like it. And thanks for watching.